All right, so I just wanted to give you some geometric insight into why we add all these extra variables, these surplus variables and slack variables, and artificial variables. And the notes have kind of explained that this is to allow us to do some geometry more easily with algebra, because algebra works better with equations than inequalities. In a sense, equations are more precise, so we can extract information from them a lot easier. The problem is, in order to do this, we have to consider only the most simplest of problems. In this case, we're looking at this example where we have a two-variable problem which only has one non-trivial constraint. And so we will add only one variable, which will put our two-variable problem into a three-variable problem. Since we can't see beyond 3 dimensions, this is as good as it gets for seeing what's happening. But this is what's happening in all problems. So we have a maximization problem. We have a single non-trivial constraint here, x1 plus x2 less than or equal to 1, and the variables are non-negative. So we add one slack variable. And again, this is what your book calls standard form, but standard form, matrix form are just two versions of the same thing. It's just how you notationally represent them. So we've added a slack variable s1. And then something I'm not concerned with is this matrix form that the book is talking about, where you actually put everything into matrices and vectors. It's kind of standard notation when you're using matrices and vectors to use some kind of notation like boldface, for example. But this problem translates into that notation as follows. We maximize C transpose X. That's just a fancy way of taking a dot product of the vector C and X. Since we're thinking of these as matrices, C is a 1 by 3 matrix, so in order to multiply it and have it make sense by X, we have to multiply it by the 3 by 1 matrix. So you just take 2x1 plus 1x2 plus 0s1, and that gives us the objective function. So in this case, our matrix A is only a single row, 1, 1, 1, because the coefficients of x1, x2, and s1 in our constraint equation. And our right-hand side of the equation is 1, and we think of that as a 1 by 1 matrix. So that's what matrix form is. It's just a way of storing the information in this way. When you're dealing with problems of high numbers of variables and high numbers of constraints, your data will be in some kind of data file or spreadsheet organized in matrices in a natural way. So you can just refer to that data file if you're writing a report. And you can just use the symbols like A, X, B to convey what you're talking about in terms of the problem. So again, just seeing how matrix multiplication works. A times X is really just the 1 by 1 matrix, x1 plus x2 plus s1. And we set that equal to B, which is equal to the 1 by 1 matrix 1. And again, our C transpose times our vector x is just 2 times x1 plus 3 times x2 plus 0 times s1. And that's just our objective function value. The real idea of what's happening is geometric. Since we had a two-variable problem, we can think of this green triangle here is our feasible set of our original problem. It has 3 vertices listed here. Again, in two variables, just the first 2 coordinates is all we're worried about. Notice that all these points here have coordinates, a third coordinate of 0, because they're on the x1, x2 plane. So this green triangle is our feasible set. By adding that third dimension with the slack variable, we've basically projected into a 3-dimensional setting. So we've taken the triangle and we've kind of projected it into this 3-dimensional setting. So this blue triangle is just kind of a copy of our original feasible set in terms of the original variables and the slack variable. And you can notice that each vertex of each triangle kind of match up. 0, 0, 0 is right below 0, 0, 1. The other two are actually the same vertices. So once we've done this, we create our tableau. So we had initially our slack variable is our basic variable, so x1 and x2 are 0, and we let our slack variable be 1. Again, my style of doing this is to put negatives times the coefficients of the objective function into the objective row so that you can see the negatives. That tells you to pivot. It tells you our solution is not optimal, and our value at this vertex or basic solution is 0. So the idea is, so really what we're doing is we've moved into this three-dimensional setting where our tableau has us standing up here at this vertex, and we can know the value, but the nice thing is we can actually see from this perspective the entire green triangle. That's what we're doing by going into higher dimensions. We're stepping out so we can actually see the entire problem. And we can basically now look at each of these vertices, the other two vertices, and from those kind of decide if they are better or not better than the value we get from this vertex. So again, there's a couple ways of doing the simplex method. The way I've outlined in the notes is a way that always works. It's not the fastest way always, but it's essentially as fast as anything else. But in this example, it's a very simple example. If you did a different algorithm, you would get the answer in one step instead of two. But the problem with that, what's called a greedy algorithm, is it tries to get the answer faster, and it often does, but there's a problem that there are problems out there where it will actually get stuck in a loop and it won't actually find the answer when an answer exists. So we're going to follow that method as I've outlined in the notes. So again, we have these negatives here. We pick the leftmost one, and since there's only one row here, we only have one choice of our pivot location. So we're going to pivot in the x1 column at this 1. So all we're really doing is adding 2 times this row to the objective row. That'll give us the next tableau. You can see that the value of the objective function has increased from 0 to 2. Our basic variable is now x1 because that's the column that's pivoted. So this 1 times x1 must be equal to this 1 on the right-hand side. And x2 and s1 are 0, so that's our basic solution. So again, think about our basic solution, 1, 0, 0. We've moved from here down to here. And again, each basic solution is matching perfectly with one of the vertices of our original feasible set. There's a correspondence there. Again, we see that this is not optimal because this negative here is telling us that another pivot will increase the value of this objective function. So now we pivot in the x2. And again, by doing so, we now have an objective row with no negatives. The value of 3 here must be optimal. This is essentially because of convexity. The feasible sets are convex. So once you find a vertex where there's no negatives in the objective row, that's telling you that none of the vertices that are connected to it by some edge of the feasible set is going to give you a better or more optimal answer. Since the set is convex, that means this is an optimal answer. And again, our basic solution here is 0, 1, 0. So after the second pivot, we moved first pivot, we went from the initial starting point here to here. We found this is not optimal, so we pivoted again, and we moved over to this other one, and this one is optimal. And the tableau at this optimal solution has basically 2 places that you could pivot to get back to either of these other vertices, but because those values here and here are positive, we're not going to get a better or more optimal value for our objective function.